All right, shall we begin? So what we would like to do today is establish a few relationships for materials that are stressed in the stress-strain curve that we're all so familiar with, okay? So what I've got up here so far is a little stress-strain curve, same kind of look as the stress-strain curve all the way back in the very first statics class that you took. It's got the same look to it there. What I'd like to do today is talk a little bit more about what happens in the plastic range of the material. Okay, so you might remember where's elastic and where's plastic. You remember? Not so much? Need a reminder? Okay, that's right. Everything over here, right, that is elastic. And then everything over here is plastic. Okay, that's where it permanently deforms if you load it up into that range. Okay, and so let's actually think about this. If you start with a specimen that I'm showing right there that has a particular area in the gauge portion and a particular length of the gauge portion, and then you subject this thing to a tensile test, right? So you basically start pulling this apart like this. Okay, it is going to stretch a little bit as a result of putting that load on there. And actually, let me make this comment because it's going to come into play several times today. Often when we draw this sort of conceptual stress-strain curve that I'm showing right here, it is not possible for us to really accurately represent everything that we want to about the linear portion of the line, linear portion of the curve there at the beginning. Okay? The reason why is that usually this slope is so steep that if I put it in proper proportion relative to the rest of the curve, it would look like it was straight up and down, right? There is very little deformation that happens in the first part of that curve relative to how much deformation happens over there in the plastic portion of the curve. And yet, we do things with the slope of that linear portion, and it does kind of stretch linearly in that first part. So usually when we represent this, we show it with a sloping line right there with then a curve that goes over the top. I just want to make the point that we very often don't show that line vertical enough so that you can, kind of infer that there is a slope that matters there. It's just hard to draw it all to scale. Does that make sense? So anyway, make that point. We'll come back to it here in just a minute. So as we begin to load this body with a force, right? We're going to kind of pull this thing apart with a force. What happens to the specimen as we start to load it that way? Okay, two things. Probably the most obvious one is that it will elongate, right? Stretched a little bit. The one that we haven't talked so much about, this is not something we really touched on in the very first statics class very much, but simultaneously to the body stretching like this, it also gets narrower. Okay? And you've seen this, like if you've ever had a piece of bubble gum, right? You take it out of your mouth and you start stretching it. It doesn't just stretch lengthwise as you begin to stretch it. What else does it do? It gets narrower in the middle, and that's because you are applying that deformation to that material. So let me take this thing and kind of line it up now that I've got it stretched a little bit, and let's actually put some parameters on here. We'll say we started with an initial length of L0. As a result of loading this thing, it's going to go to a new length in this gauge portion of the material. It's going to go to a new length there. And just because I don't want to come up with, too hard to understand terminology here, let me just call this L new. Okay? So we get to a new length. Also, at the same time, there's a different area that we've now, caused to happen on this middle part, this gauge portion of the material. And we can call that maybe A new. Okay? And my point that I wanted to make here is that, especially by talking about that vertical line, the linear portion of this curve is almost vertical. as we load this into the plastic range, most of the deformation is going to happen after the material has plastically started to deform over there in the curved portion of this thing. And there's a relationship here that it basically tends to hold, even though it's not exactly true. There's a relationship here that the material that composes the gauge portion of this thing maintains almost constant volume. Okay? So almost constant volume. And it's one of those that, you know, you've seen this happen in several of your engineering classes. As soon as we can say that it's almost, then we just say, well, let's assume that it is, right? It is constant, even though it's not quite exactly constant as you begin to load this material. Okay? Well, that's actually an interesting relationship, and we'll look at it in more detail in here in just a second. But that relationship, that volume stays almost constant, means that another thing that we can do with this stress-strain curve is, instead of talking about there being a particular strain, we can talk about there being a reduction in area, right? Because at the same time as the part's stretching, I can maybe put down here also reduction in area. Okay, because as the strain begins to increase, you're also going to have a decrease in the amount of area that's there. And so those two things are related to each other, and they're basically related linearly enough to where you can still say that the curve more or less looks the same, right? As that area decreases, the strain increases. Okay? All right, so this is, you know, so far so good. Here's a question for you. What if I take that specimen and I apply some amount of force to it that causes it to deform up into the plastic range? So let me actually draw that on here and say, let's look at a little line here, right? It goes up into the plastic range, and I take it not quite all the way up to where was the ultimate strength of the material, right? This used to be, we call this the ultimate strength for this material. Okay. What if I don't quite make it there and instead unload it once I get up to this point? What happens now? Okay. It will unload. What happens is we get back the elastic portion of its deformation, right? So there's a line that's parallel with that linear portion of the curve, and it unloads along that line, and then what we're left with is some permanent deformation. Okay? So this right here, if I load it up to this point and then unload it, this would be permanent deformation. Yeah, make sure I spell that right. Permanent deformation. All right. Well, here's a question for you now. So we loaded it up to that point, and then we unloaded it, and now we actually have a specimen that is a new length, right? It didn't go back to its original length. It now has undergone some permanent deformation. It's now a little bit longer. What if I then forget all about that test that I did, I throw that specimen into a drawer, right? And a year later, someone else comes along and wants to do a tensile test on that specimen. They don't know anything about what just happened with respect to the first test that was done on that specimen. Okay? Yeah, he's got a good point, right? Is their stress-strain curve going to look the same as the first stress-strain curve would have looked if you had tested it all the way to failure the first time? Why not? It's deformed. There's a couple things that are now different about it. One of the things that's different is that area has now been reduced, right? So when you think about this stress axis up here, stress is what? Force over area, right? So think about this axis up here. What you've done for that specimen is you've actually reduced the amount of area that is available to carry the load. So if you put the exact same amount of force as you did before to get up to that point, right, That's where it's going to start yielding again, right? But if you think about that, that exact same amount of force, because this is engineering stress and strain, we don't update what the value of the area is as it deforms. We just take whatever that original area was when we evaluate an engineering stress or for an engineering stress kind of a calculation. Well, now we know nothing about what the original area was. All we have is this new area because we just pulled this thing out of a drawer and we measured it. What's that going to do to the amount of stress that we calculate for our new stress strain curve now that we've pulled it out of the drawer and tried to start testing it again? Okay, area will have gone down. What is that going to do to the amount of stress that I calculate? It goes up, right? So that's kind of interesting. Stresses are going to now look larger than they did before because that amount of area has reduced. Anything else change? What's the calculation for strain? Okay, engineering strain is change in length over original length. Well, now we've pulled this thing back out of the drawer. We have a different original length because A new is now our original length for our second test, right? So what does that do to my strain values? Yeah, I'm increasing the denominator, right? It's going to start making that axis look more compressed, right? So what happens with this stress-strain curve is it starts to look a little bit different. Let me draw it with a little bit different color here. It looks now, let me get a little bit darker. It looks now like a curve that looks something like this. Okay, comes up here, and it's going to start curving over, but it's not going to make it as far, right? And that's what my stress-strain curve will look like for the new piece of material, or this material that I pulled out of the drawer after someone did the first test on it. Well, that's kind of interesting. One of the things you can immediately see is, what would I evaluate the ultimate strength value at? It's higher, right? That ultimate strength value has now increased as a result of that initial test that I just did. Okay? Now it's kind of cheating a little bit because we got that reduction in area as we were loading the material, but it's not really cheating because that is truly a process that can be done to materials to strengthen them, right? It's still a specimen that's that shape. It's, we've reduced that cross-sectional area. You can kind of think in your mind, what if we, for our parts that we decide to produce for actual usage, what if we decide to do processes like this before they're put into usage? That will actually increase the strength of the materials in order to make them stronger. And so this is something that is done quite often. As a matter of fact, there's a word that's given to this. It's called cold work. Have you heard of that before? So cold work is where you intentionally deform materials at kind of room temperature, right, at low temperatures. That's important because if you do it at higher temperatures, what you can do is you can actually relieve some of the internal stresses that would cause these materials to actually increase in strength. So that gets a little bit deeper than I wanted to go today, but that's why it's called cold, is you have to do these at basically lower temperatures so that it really is just a plastic deformation that you're applying to the material without heating it up to sort of relieve some of those internal stresses that could happen inside of the material. Okay, so let me just put that up here. This has now been cold worked. Okay, and I pointed out that the new ultimate strength has now increased by a certain amount, right? That's kind of a net increase there of the ultimate strength. Okay, that's shown right there. Did any other kind of strength increase? Okay, for the original material, if we were going to draw a line that would show where we sort of left off in terms of, the yielding strength, we would have said it had been right about there, right? That would have been the original yield strength for the original specimen. We still have the same specimen, but now it's been worked a little bit. We throw it back in the machine, we try to test it again. What would we say the yield strength would be now? Okay? it's going to go up to some new value, all right? I don't know, we'll just use this red, okay? Our yield strength has now also increased, okay? Yeah?
So does that mean you're technically increasing its amount of elasticity, but for a specific frame of reference?
Okay. So I think what you're, let me see if I can rephrase that, okay? His question is, did you just basically increase how much it's in its elastic range? And that is actually a pretty good way to describe it, all right? You've basically increased how much stress can be applied to the material before it begins to plastically deform more, right? And you can kind of see that on the original figure. Like, what if you did know all the history of this little specimen and then you loaded this thing again, right? So let me grab yet another color here. Now I'm going to load this again, and now this time I load it, it's going to load along this line. And you can see there that that yielding strength has increased because it's not really going to yield as I reload it along this line again. Now it goes all the way up to that point right there before it begins to further plastically deform, okay? And what you'll notice, another thing that happens there is you will have gotten a lot closer, your yielding strength will have gotten a lot closer to your ultimate strength because you've used up some of that plastic deformation that it can withstand, okay? Does that kind of make sense? So this is what you do with these materials in order to try to intentionally cold work them in order to be able to increase their strength. Okay? So let me actually show you another thing, because this, a lot of times gets people thinking about maybe engineering stress and strain aren't really the best way to try to describe how close we are to breaking the material, right, with stress. Because what happens is this area is actually decreasing as we start to load it. So would there be a way for us to do a different way of evaluating stress that basically allows us to update that area kind of in live time as it is deforming? Because that's a better representation of how strong the material has actually become, right? And such a thing does exist. It's what we call true stress, okay? And what you do with true stress is, instead of taking the force over the original area, you take force over the current area, right? And that gives you this idea of a true stress. True strain is another thing that's possible for us to come up with, because you think about this, with strain, what we're trying to do is come up with how far have the individual particles of the material had to move relative to one another, kind of as it begins to slip, how far have they had to move relative to one another. And one of the ways that we can deal with that kind of, especially at a very local level, because one of the things that happens with this body as you begin to deform it here is it undergoes what's called necking at some point, which means that it starts to deform locally at a particular location a lot more heavily than at the other locations. In order for these relationships to hold, we kind of need to focus in on just the area of material that is the worst, right? And in order for that to make sense, it no longer makes sense for us to always use the original length. What we need to do is locally look at one little spot and say, how long was it at first? How much has it changed in length, right? And if you actually evaluate that sort of in live time, you can come up with what's called a true strain, okay? And here, let me put these down here. True stress, okay? This is basically force over actual area, right? At any given point in time where you're starting to stretch it, it's whatever the actual area is at that time, as opposed to the original area. True strain, this one's a little bit harder to define, but this is how it's defined. What you do is you take an integral from whatever your original length was up to whatever your new length is. And what you're going to do is, at any given point along that process of it elongating, you're going to look at little changes in length, dl, and each time, for each one of those little tiny bits of increase in length, you're going to divide by whatever the current length was at that time. And what the integral does is it evaluates that over the entire deformation that it happens, or that it goes through. Okay, what's interesting about this integral can be further evaluated, and what you'll find there is that that integral is just going to be equal to the log, natural log, of what? Okay, L nu minus the log of the original length. Okay, that's what the integral would say. But by the rules of logarithms, what is that? Okay, you would have the log of L nu over the original length. Okay, so these are some good things for us to know, is that these true stress and true strain are some things that we can evaluate. And let me actually do this too. I'm going to give myself a little bit of room here. Let me kind of show you what these two curves might look like, right? So if this is a set of stress-strain axes again, and we would have our original engineering stress-strain curve, something that looked like this. Okay. What true stress and strain look like is that it kind of starts off being somewhat similar, but then this curve comes up like this and doesn't ever curve back down. All right? Because the reason that the engineering stress-strain curve curves back down is the fact that you've got this reduction in area. It's not that the material is actually weaker. Does that make sense? So this goes up here and then would eventually break up here. So this is true, and this is the engineering version, which is, you know, simplified like we often do in engineering kind of stuff. Okay? Now let me actually say this too. What if your job was to actually try to characterize how these materials would begin to deform, and you know that one of the things that can happen there is that the middle of the specimen might start to neck like this? How do you handle that? Because now, let's say that you're measuring for these L0 or L nu, you're basically measuring from this point to this point. You're missing, with that information, what exactly is going on this little necking portion of the specimen, right? You're not getting that because what you're measuring isn't actually giving you what's happening locally at the neck. What could you do about that? Okay, you might be able to try to do something to measure that little region specifically, right? And eliminate the other parts of the material and focus in on that little region. But what if you don't know where that region is going to occur? Which you kind of don't with these specimens. You don't necessarily know where exactly that necking is going to happen. Well, let me show you a possible solution. What do you think they're doing in that picture? Okay, what they're doing, those two things you see pointing at that specimen are lights. You're trying to get plenty of light on the specimen. What's this thing down here? That's a camera. So what are they trying to do? What they're probably trying to do is measure that specimen with that camera and get those values as best they can. And one of the things that they are going to be able to find with that is cross-sectional area as it begins to deform, right? And with our relationship here that we're about to look at, we're going to be able to transform between actual strain and reduction in cross-sectional area, at least up to the point where it starts to neck. And once it starts to neck, then you have to sort of just look at the cross-sectional area. It may not relate to overall strain of the whole specimen. Okay, but I wanted to point out that at some point it might make sense, instead of trying to measure strain directly, it might start to make sense to measure cross-sectional area instead of directly measuring strain in doing one of these tensile tests. Okay? All right. There's another little thing that I want to get to here, and it is a relationship between engineering stress and strain and true stress and strain. So let's start with strain right here. Okay. What's the original definition of strain? You guys said it just a second ago, right? For engineering strain, which I'll just leave without subscript. It's going to be equal to the new length minus the original length over what? Original length. Well, let me do something before I get into the rest of this. Let me kind of manipulate this around a little bit. You'll notice here that I could just divide L new by L0 and L0 by L0, right? So this ends up being what? Okay, L new over L0 minus 1. Okay, this is our engineering strain. Well, what if I actually change that around even one more time, and I say this means that L new over L0 is going to be equal to strain plus 1. All right, engineering strain plus 1. Okay, now you might see here that this might actually cooperate pretty well with one of these things I said just a second ago. What's true strain? It's the natural log of L new over L0. So let me put a sub t down here, meaning that's the true strain. Okay? This is just going to be equal to the log of L new, just like we said a second ago, over L0. This is simply going to be equal to the log of what? Engineering strain plus 1. So if you want to transform from engineering strain to true strain, there's a fairly simple relationship that will let you get there, just by taking the log of that engineering strain plus 1. Okay, so far so good? Well, let's do another thing here. Okay, let me look at stress. What's our definition of engineering stress? Okay, force over area, but the area that we use is the original area. Okay? Well, what if I change this up and I want my true stress? How do I get my true stress? Force over actual area, which let me call that A new, right? Because that's where it got to with this test that I just showed you. Okay? Well, that's kind of interesting. Let me add one other thing in there that I mentioned a second ago, but I'll put it in here kind of formally. We assume very little change in volume. So if that's the case, then what we have is that our original length times the original area in the gauge portion should be equal to what? L new times A new, right? Because we're just calculating the area of that cylindrical part that's right in the middle, the gauge portion of the material. And so the length times the cross-sectional area is the volume in both cases. Okay? Well, let me take this and actually manipulate it a little bit. Let me say I want to find L new over A new. What will this be equal to? Okay. Actually, I meant to write, excuse me, sorry. I meant to write L new over L0. Sorry. Okay, what will this be? Okay, it'll actually be inverted from each other, right? A0 over A new. Okay, that's kind of interesting. That might be useful over in my true strain equation. What else could I say about my true strain equation here? Log of L new over L0 is going to be equal to the log of A0 over A new. That's kind of interesting. And both of those are equal to the log of engineering strain plus 1. Okay? Well, I could actually manipulate this even a little bit differently, and I could solve it for A nu, right? So this is one of the places I can go with it. What's another place I can go with it? A nu, what will that be? Okay, is that what you're saying? Okay. I agree with that. What if I plug that in to my true strain equation right there? Right? What will this give me? Okay. L nu over, okay, L naught. All right. Well, that's kind of interesting. What is L nu over L naught? L nu over L naught is engineering strain plus 1. What's F over A0? Engineering stress. And this is what true stress is. Okay? So we've got a few relationships here that I wanted to kind of walk us through. Some of these, some of you may have edition 11 and some of you may have edition 10. I didn't know it until today when I started going through some of this. Edition 11 actually expanded a lot of this material that I'm touching on today. Edition 10 didn't have some of this stuff in it. So, you know, good news for you, I guess, if you have edition 11. But here it is. All right. I think that's about all the background that I wanted to touch on before we start doing the example problem. All right? You guys ready for that? Got a lot of text. You don't feel like you have to get it all down exactly because I did upload this to Moodle. In case you miss anything, don't get it exactly right, you'll be able to go back and look and see what it said. Okay, we're dealing with this annealed 1144 steel. All right. If you actually look in some of the literature, this is a steel that is very similar to, if not actually, you know, occasionally maybe it is, a steel that has a kind of a marketing name called stress proof. That's kind of interesting. So anyway, you might care about that, you might not. But it's a material that actually is very good at work hardening, right? It's a material that's very good at gaining strength through cold work, okay? But anyway, you don't necessarily care about that. It has an initial gauge dimension that's shown, right? The initial gauge dimensions are 20 millimeters of diameter and 100 millimeters of length in the gauge portion. All right. What then happens is we're going to apply a load to it of F, and then we are going to remove that load from it. And after having done that, the new length of the specimen is 109, or I should say, not of the whole specimen, of the gauge portion of the specimen goes to 109 millimeters as opposed to 100 millimeters. Okay, so it got this plastic deformation by stretching. And what we're going to do is find all of this stuff. Part 1, Part A, the engineering strain and the true strain after unloading. Part B, the original gauge area and the new gauge area after unloading. The cold work factor, we're going to look at that here in just a second, what that is, but the cold work factor for the gauge portion of the specimen. The engineering stress and the true stress that the specimen held while it was fully loaded. The new yield strength and the ultimate strength of the gauge portion of the material. And then finally, the approximate Brinell hardness before and after the cold work. That's what we're going to try to find, is all that stuff. Okay? And one of the things I'm going to say before we even get started is this. There are two ways you can handle this. One of them is you can make an assumption that all of your deformation that happens is plastic. The other way you can do it is you can try to do some kind of an accounting for the amount of elastic deformation that happened in the material. And I'm going to go ahead and give you some good news. I'm going to allow y'all to kind of consider all of the deformation for these cold work kind of problems to have been plastic, to where you don't have to try to consider what happens with the elastic portion of the deformation. All right? It's actually a little bit trickier than you might think to have to deal with the elastic portion of how much the thing deforms, believe it or not. Okay, shall we get started? Part A, the engineering strain and the true strain after unloading. These aren't too hard. What's the engineering strain? Okay, final length, 109 millimeters, minus 100 millimeters, over original length, 100 millimeters. Okay, so when I plug all this in, what we should end up with for our value is 0.09. Units? Don't need any units on it. It's millimeters per millimeter. They divide out. Okay? That's part's easy. What about for the true strain? What's our formula for that? Natural log. Okay. Right. The new length. Over the original length. And when we punch that in, what we will end up with is a value of 0.086178. How does that compare with the engineering strain as far as its size? Are we saying there's more true strain or less true strain than engineering strain? Less. Yeah. Is that what we expected? It is, right? Because what we're doing is we're kind of updating in live time what that original length is for each little increment of more deformation that happens, which means we're constantly increasing the size of the denominator, right? Which means you're going to end up with less strain that we will have predicted, okay, for true strain. Okay, good so far? Part B, the original gauge area and the new gauge area after unloading. Okay, so part B, what's the original gauge area? $20 millimeter diameter. So we have pi times 20 millimeters squared over 4. That's not going to be earth-shattering for anybody. This ends up being 314.16 square millimeters. Now, how do I figure out my new area? Okay. Well, we could try to manipulate it down, or we could just write it this way, where we know that that relationship of the true strain that we just found, right, is going to be equal to the log of the original area over the new area, right? So what I can do here is I can plug in 0.086178. This is going to be equal to the natural log of, what was it? Original area over new area. The original area was 314.16 square millimeters. And the new area is what we're trying to find. Okay? And again, I don't want to waste too much time on doing things that you already know how to do, but you can plug that into your calculator. You know, you have calculators, most of you in here, that do single variable solutions. You can plug that in and find that area, right? My only bit of advice is make sure that you're picking an area that's, as an initial guess, that's not too far out of bounds for what that is, because the log function can be a little bit sensitive to what exactly you plug in, right? And so then the numerical solution inside of the calculator can be a little bit tricked by, or it can get messed up by putting a bad initial guess value for A new. Anyway, after you solve this, A new turns out to be 288.22 millimeters squared. Okay, whereas my original area is 314.16. Does that surprise anybody that it changes that much? I don't know. Early on when I started looking at these, it kind of started to surprise me just how much you could stretch something like this and how much the area would change in response. All right, so there's my original area and my new area. Part C, the cold work factor for the gauge portion of the specimen. So cold work factor is one of these numbers that is actually used, believe it or not, a pretty good bit out there. And a lot of times you use the phrase percent cold work. It's the same thing as this cold work factor. It's just expressed as a percent instead of as a decimal. Okay? So anyway, the definition of the cold work factor, if you're working in, if you're working out of the edition 11, is going to be on page, here it is, page 56 in edition 11. In edition 10, it's going to be on page 50. Okay? And it's given with equation 226 in edition 11. In edition 10, it's given with equation 212. Not 212, excuse me, 213. Okay, here's the definition. All it is it's going to be equal to the original area minus the new area, if we use our terminology here, that's what we'll call that, over the original area. Now you might notice, you know, and you'd have to follow through with how they actually define this in the book. They give you in that same equation that this cold work factor, you can either use the term they use for my A new, they use A sub I, but they have one that's A sub I and one that's A sub I prime. Okay? And if you dig into the text a little bit, as a matter of fact, there's a picture that might explain that a little bit better. The picture is figure 2.6 in edition 11. Basically, the difference between AI prime and AI is whether or not they took into account the elastic portion of the deformation, right? And so just the fact that they are saying that this can either be AI prime or AI, and that they don't really care in this equation for cold work, that's further sort of confirmation that we can probably safely ignore the elastic portion of the deformation, and it won't throw us off much, okay? All right, so what do we do with this? We're going to plug these values in, right? 314.16 square millimeters minus 288.22 square millimeters, all over 288.22 square millimeters. Oh, sorry. Thank you. I wrote the wrong number down. What should I put in the denominator? Yeah, sorry about that. I shouldn't have put the new area there. 314.16 millimeters squared. Okay. And if I calculate that out, the amount of cold work that I'll have here is 0.08257. okay? And like I said a second ago, the other way of talking about cold work, this is the cold work factor that they're talking about here. Sometimes you will see someone express this as being 8.257% cold work. Okay, same thing. All right, any other comments before we move on to part D, finding the engineering stress and the true stress that exists in this material when it's fully loaded? In other words, before, it says at the beginning up here, we're going to put this load on it and have it stretch, and then we're going to release it. How much load did it actually take for us to get up to that point to make it, you know, not load, but actually stress? How much stress did it take for us to make this thing stretch like this? Okay? What you're going to find here is that there's an equation that is given in the text, and I'll show you for edition 10 on page 50, equation 215. Okay? That same equation, they kind of presented a little bit different order and stuff in edition 11, but you can see basically the same idea of that equation in 230 in edition 11. All right, and here's what it says. Once you get up into the plastic range, the amount of stress that you're going to see is going to be equal to this coefficient called sigma 0 multiplied by the true strain. Okay, I'll use my terminology here of the true strain, raised to an exponent of m. Okay, now let's look at this sigma naught and m. Those are factors that, at least for a few of the kinds of materials that we have in this textbook, have been tabulated for particular kinds of material. So if you look back in table A22, okay, A22 for 1144 steel, it tells us here that our sigma naught coefficient is going to be 992 MPa. Okay. We can take this and multiply by the true strain that we have, 0.086178. Okay, and raise that to the exponent that's listed in the table. The exponent, the strain strength exponent m, is going to be equal to 0.14. All right, to kind of give you an idea of what it is that we're doing here, it turns out that the kind of curvy portion up at the top of the stress strain curve, if I go all the way back up and show you that again, this portion up here can be described with that equation that I just wrote down. Okay? Tricky part is it is true stress, true strain, right? And another tricky part is it really kind of applies to just plastic strain, not plastic plus elastic strain. Okay? But what did I say about what we're going to do with the elastic strain? We're going to kind of ignore it. So we're just going to not worry about that part of it. You can see how this would be a little bit more tricky if we had to figure out how much this whole curve shifted over as a result of the elastic deformation, right? What I'm going to let you do is just ignore that part because it actually gets you pretty close, because that line tends to be pretty straight up and down for the elastic portion of this curve. Not perfectly straight up and down, but it's pretty close relative to the rest of the deformation for most materials. Okay? So anyway, what we just did there is we found that true strain that existed after we unloaded the material, which is pretty close to the true strain that happened when it was at its full load. And we're going to plug that in here to get the amount of stress that it must have taken to make it get to that point. Does that make sense? Yeah.
What table is this
Okay, that information, those two factors, those were out of table A22. Okay, so when I plug these in, what this gives me is 703.8 MPa. Okay, and this is a true strain, because that's what that curve is giving you, is true stress and true strain. What do I need to do if I want to transform that into engineering strain? Because that was what was asked for up here. It says the engineering stress and the true stress while fully loaded. I don't know, I may have said strain a second ago, right? If you're trying to go from true stress to engineering stress, what do you need to do? Okay, that's right. This relationship right here says that if you're trying to get engineering stress, you can just take your true stress and divide by your strain, engineering strain, plus 1. Okay, so down here, if what I'm trying to get is my engineering stress there, I take my true stress, 703.8 megapascals, and divide it by my engineering strain plus 1. Okay, and that ends up giving me 645.71 MPa. Okay, now this is kind of interesting. If you'll look in table A22 again, at 1144 steel, other parameters it gives you there, it says yielding strength is 358 MPa, and ultimate strength is what? Anyone see that? 646 MPa. Right? So we loaded this up to an engineering stress of 645.71 MPa. I got it pretty close to its ultimate strength, but I didn't quite get there, right? And therefore we've cold worked it a pretty good bit, right? We've gotten it pretty far up there along its curve to the point where it almost got up to its ultimate strength. Okay? All right, let's move on to the next piece, right? It says here, the new yield strength and ultimate strength of the gauge portion material. Okay, tell you what, before I get there, I actually did want to take a little pause and show you that I wanted to show you what these curves actually look like when they are plotted proportionally, right? So I did that. Okay, so what you're looking at here with these curves, you're looking at the red curve there is the true stress, and the blue curve there is the engineering stress, right? And you see how the engineering stress curves back down. In case anyone's curious about where those came from, I have some equations right here that are used to plot these functions. Now it's kind of interesting here. I can plot true stress against true strain, or I can plot true stress against engineering strain, right? There's two different options there. And it's one of those that if you want to compare a particular strain value and be consistent from engineering strain to true strain, you might want one thing. But if you want the curve to look proper for being true stress versus true strain, you might want the other thing. So one of the things I did, in case you guys like Mathcad, what I did there is I made both equations in there. One of these equations plots true stress. That one right there plots true stress versus engineering strain, right? If I want that one to control, I can just pull it down a little bit, and it'll change what that curve looks like. Otherwise, I can move it up And the other one that might control is this one over here, where it plots true stress versus true strain. Does that make sense? How much difference does it make? Look, do you see what happened with that curve? See that? Not a ton, but it made a little bit of difference, right? The curve isn't exactly the same. It makes a little bit of difference to have, plotted, versus true strain versus engineering strain. You can see there, I used all those transformations from engineering to true stress or strain, given, whenever I tried to find these curves. Okay, what do you think that green line is? Okay, so the green line represents basically the unloading line. So what I did with this material is I loaded it, and I should be a little bit careful here. These curves aren't exactly correct over here because see this little blue line, this little light blue line that goes over here? That is that 0.2% offset that we usually use to define where a yielding strength is. And that, if you look at where that line intersects with this purple line, which is the yielding strength, that gives you about how far these curves should have shifted over in order to account for that elastic portion of the curve. Does that make sense? How big is that? It's very, very small, right? So we don't necessarily care about it that much. We're going to be pretty close without having to account for that little bit of change that happened right there. But anyway, where I was going with that is that basically this is going to load along kind of this a line really close, this blue line, come up along this curve, and then when we get up to this point, it's going to unload along this green line, right? And so the stress values that you see at these two locations are going to be pretty close, if not exactly, the values that I just calculated for my two stress values when it was up there loaded. It's going to be the engineering stress and true stress at that point. Okay? The other thing that I'm going to mention before I go back off of this picture is that I went ahead and plotted these curves all the way out to an amount of strain that it says in table A22 this material can withstand. You might see the very last entry in there. It says fracture strain of 0.49. See that? So I had these curves end at the point where we expect that strain is not going to be able to strain anymore, right? That was how much it strained before it fractured. And by the way, I suspect that value in the table, based on running some calculations on this, I suspect that those are actually true strain values for that fracture strain, not engineering strain. Okay, let me go back to the problem that we were solving here a second ago. We have a few more pieces to do. The new yield strength and the ultimate strength of the gauge portion material. Okay, well, guess what? The new yield strength, okay, that new yield strength can be calculated exactly the same as we just calculated this right here. Why is that? Okay, go back to that picture. The true stress that occurs where this thing got up to right here is exactly the true stress that it's going to take if I unload it along this green line, then load it again. It's the exact same stress where it's going to then start cutting over, and so that's going to be the yielding strength, right? So it's literally the exact same calculation that I just did. The yielding strength has increased up to the point where this green line is intersecting with that red curve, which is exactly the calculation I just did right here, okay? And you'll see that like in addition 11, the equation is 230, and it says that SY prime is going to be equal to sigma naught times your true strain raised to the m. Okay, so this is just the same as it was before. This just ends up being 703.8 MPa. Okay? Now, SU prime. This is the new ultimate strength that happens as a result of this cold work that has been done. There's another equation in addition 11. This is equation number 232. And it says that this is just going to be equal to the original ultimate strength divided by 1 minus this cold work factor. And remember, the cold work factor is basically just a way of accounting for the reduction in the amount of area. So really all we're doing to find the new ultimate strength is we're accounting for the fact that now we can carry the same amount of ultimate load, like the actual force applied to this specimen didn't change as from its original. Remember back in the beginning? We tested this thing, then threw it in a drawer. Anyone who pulls it back out of the drawer and tests it is going to get the same amount of force to break that specimen in two as before. What changed is the cross-sectional area. Okay? So that's what you see in this equation down here. 1 minus W, right? That accounts for the change in the cross-sectional area, which is what causes this increase in ultimate strength. Make sense? Okay, so what we do is we plug this in. The original ultimate strength value was in table A22 at 646 MPa. The cold work factor was 0.08257. And when we plug these in, what we end up finding is 704.14 MPa. Now, is that interesting? Look at those two numbers together. Okay? Here's a good question that I want to answer also. If you load it to the point where it actually begins to start necking, meaning the place beyond which you've gone past that ultimate stress of the original stress-strain curve, can you do that to a material? You might be surprised. You actually can, right? You don't do it in the same context as a tensile test, because with a tensile test, you assume you put that load on there, and once it gets up to that value, it's just going to pull apart and break pretty quickly once it starts to neck. But you can set up a manufacturing process that doesn't continue to pull, but it can apply more cold work that would exist beyond that point where it would have gone to its ultimate strength. What do you think happens to yield strength and ultimate strength relative to each other once you get past that point? They'll be the same as each other, and you will have a brittle material, right? But you can actually do that to a material. It's just they'll be the same as each other, and you won't have any sort of additional plastic deformation that can happen. It'll just break when it gets up to whatever that load is that would cause it to break. Okay? All right. Let me give you the last couple of things before I let you go. F. These are pretty easy, but once you know the ultimate strength of a material, there is a relationship that allows you to find or kind of relate it back and forth to the hardness of a material. And a lot of you may have done like a lab in 215. You guys remember doing MEEN 215, and you did a lab where you did hardness testing. Basically, it involves pressing an indenter into a material, and then you could find some information pretty easily about that material without having to do a full tensile test. All I wanted to do is just show you here that we can find the Brinell hardness before this cold working. This Brinell hardness is going to be equal to the ultimate strength before divided by 3.4 MPa. This is based on equation 236 in addition 11. Okay, I don't remember what it is in addition 10, but actually I do. Equation 221. Yep. There's just a linear relationship that gets you pretty close. This isn't a perfect relationship. There's some scatter in the data, but if you want to have a good estimate, you can just use 3.4, right? So this ends up giving you 190 MPa. whereas HB prime, do the same thing, you just plug in SU prime over 3.4 MPa. This is going to end up giving you 207.1 MPa. Whoop, and I should not have put MPa there, excuse me. This is just a Brinell hardness number. Okay, so that's part F. All right, cool. Thank you all for your attention, and I will see you guys on Wednesday.